A 250-ton freighter touches down in under 1,400 meters, half the runway a 787 requires, walks away unscathed. Watch what actually happens in the final 6 seconds before the wheels hit the concrete surface below. The nose drops, the flaps extend to their final notch, the engines spool up, not down, before touchdown. A 400-ton machine loaded with mining equipment bound for the Arctic settles onto concrete shorter than a suburban street. A passenger jet of nearly identical weight at the same airport would still be climbing through open air. It would still need 600 meters more of pavement. It would abort the approach and circle back. So what does the freighter know that the airliner does not? The answer surprises even seasoned aviation engineers. It is not what most engineers and almost no travelers will ever tell you. It is not weight, it is not about brakes, it is not even entirely about the pilots working the controls up there.
The real reason cargo aircraft land on runways half a passenger jet's length is a decision made decades ago. A decision baked into the airframe, the certification paperwork, and the very definition of what this aircraft exists for. To understand it, we have to leave the terminal behind. We travel to places most passengers never see. Every hour, more than 100,000 tons of freight lift off from airports around the world today. Some cargo moves through the polished hubs of Memphis, Hong Kong, and Leipzig, gleaming beneath halogen light. But a surprising share lands in places that would terrify almost any commercial captain flying passenger routes today. Gravel strips in northern Canada, dirt fields across Central Africa, ice runways scraped across frozen Siberian lakes, mountain airstrips carved into Himalayan valleys, where the pavement ends abruptly at a 1,000-meter cliff edge below. These are not exceptions.
These are the arteries of a global logistics network that never stops moving forward, keeping mines running, hospitals stocked, armies supplied. Subscribe to continue exploring how our modern world truly works. The stakes are enormous. A single flight into a remote clinic can carry 6 tons of vaccines. A single freighter arriving in a war zone can deliver a full battalion's worth of rations overnight. A single cargo run into a mining site decides between a functioning economy and a collapsed one. And every one of those critical missions depends on a variable most travelers never consider: runway length. Runway length is not just a technical specification. It is an economic lever hidden in plain sight. A 1,000-meter airstrip costs a small fraction of a 3,000-meter one and requires far less land and concrete. It needs less drainage, less lighting, and it can be built in 6 months instead of 6 years. It can be placed almost anywhere.
Which means the aircraft using it unlocks entire regions of the planet. But here's the thing. The physics of stopping a heavy jet on a short runway should be impossible. And the first contradiction hides inside the landing gear itself, a mechanical secret hiding in plain view. Consider 2 aircraft that share almost identical DNA, the Boeing 747 freighter and the 777 passenger jet.
Both are wide-body giants. Both weigh at maximum landing weight somewhere between 200 and 300 tons. Both use 4 sets of massive main gear tracks and are certified to identical international safety standards. And yet the freighter, on paper, needs roughly 1,500 meters of runway to land at full weight. The passenger jet needs closer to 2,400 meters, nearly a full kilometer of difference between siblings. Pilots use a number called VREF, the reference speed at which aircraft cross the runway threshold on approach. On the passenger jet, VREF is deliberately optimized for smoothness, margin, and passenger comfort above all else. On the freighter, VREF can be flown 5 to 10 knots slower, and the descent path can be steeper. That single adjustment shaves hundreds of meters off the ground roll. It sounds small, but it is not. In aviation, energy scales with the square of speed. A small change at touchdown reshapes the entire stop.
A 5% reduction in touchdown speed produces nearly a 10% reduction in total stopping distance. The naive answer, of course, is weight. Lighter plane, shorter stop. But that answer collapses under scrutiny. Some freighters land heavier than their passenger equivalents, and some passenger jets land lighter than their freighter cousins. And still the freighter stops shorter on every runway. The naive answer is weight, and it is wrong. To find the real answer, we have to go back to basic physics, because physics sets the ceiling. Physics defines what is possible. Everything else, every clever design, is engineering breaking through that ceiling. An aircraft on final approach carries an enormous amount of kinetic energy, proportional to mass and velocity squared. To land, that energy must be dissipated. Some bleeds off through aerodynamic drag as the plane slows down. Some of it is absorbed by the landing gear on touchdown, cushioned by struts compressing under enormous force. But the vast majority, often more than 80%, must be converted directly into heat by the brakes. Modern carbon brakes on a heavy jet can reach temperatures above 500 degrees Celsius during a single stop. Hot enough to glow. Hot enough to boil hydraulic fluid. Hot enough that, on rejected takeoff, they catch fire. Runway surface matters just as much. On dry concrete, friction between rubber and pavement measures roughly 0.7. On wet concrete, it drops to 0.4. On packed snow, 0.2. On glare ice, below 0.1. The same aircraft at the same speed with the same brakes can require 3 times the distance to stop. Deceleration is not a natural process. It is engineered, calibrated, and paid for in millions of dollars. This is where the freighter diverges from the airliner. Physics sets the ceiling, but design breaks it. Here is what they don't tell you at the airport. The real reason cargo jets land shorter, it has almost nothing to do with technology and everything to do with the aircraft certification profile. When a passenger aircraft is designed, comfort is a hard constraint, not a preference, an engineering constraint.
Approach angle is limited to roughly 3 degrees because steeper descent would push travelers into seatbelts and spill drinks. Descent rate at touchdown is kept near 200 feet per minute for a comfortable, smooth passenger landing. Hard limited at 600 feet per minute, beyond which mandatory structural inspection of the airframe is required. G-load on touchdown stays below 1.4 times gravity. Turbulence tolerance is high, bank angle conservative. Every one of these numbers is a runway extender in disguise, quietly stretching the concrete they require. A freighter operates under a completely different rulebook. The cargo does not complain. Steel pallets do not spill coffee. Automotive parts do not need a smooth landing. So the freighter can be certified for far steeper approaches, sometimes 4 or even 5 degrees. It can absorb touchdown descent rates twice as harsh as any airliner. It can be planted onto the runway with intent, so weight transfers immediately to the gear and brakes. On a passenger jet, that landing would trigger mandatory inspection. On the freighter, it is simply Tuesday. There is a term for this in aeronautical engineering: dispatch tolerance. It measures how much stress airframes accept. Cargo airframes are certified for far higher dispatch tolerances because they operate into short, austere, imperfect airfields daily. That relentless duty cycle continues for 30 years. Comfort is the hidden runway extender that no one talks about. Once you remove passenger comfort entirely, every other system on the aircraft quietly changes. Consider the reverse thrust system. On a passenger jet, reverse thrust is only a supplement. The aircraft can stop without it at all. On a freighter, especially a military-derived design, reverse thrust becomes the primary deceleration tool, deployed aggressively every landing.
It is calibrated to bite harder, deploy faster, and hold much longer than any passenger equivalent in service. Some cargo aircraft can even use reverse thrust to physically back themselves along the ramp, no tug required. Carbon brake stacks are thicker, absorbing more energy per landing, at the cost of a shorter service life. Anti-skid systems are tuned more aggressively, letting wheels skirt right to the edge of lockup for maximum friction. The trade-off is severe tire wear. But tires cost far less than lengthening any austere runway ever could. The high-lift systems tell the same story. Flaps and slats deploy to far more extreme angles on freighters. This generates enormous lift at low speeds, letting the aircraft cross the threshold slower, land slower, stop shorter. On passenger jets, those flap angles would generate unacceptable noise, vibration, and drag. On a freighter, none matters.
The landing gear itself is reinforced. Larger struts, heavier oleo pistons, sometimes an additional bogie for rough terrain. The C-17 Globemaster, a military transport built by McDonnell Douglas, was engineered from the ground up for exactly this. It has 28 wheels distributed across its main gear and can land fully loaded on unimproved dirt strips. It stops at maximum weight in under 900 meters, then reverse taxis off the runway using its own power. The Antonov AN-124, the Soviet-designed heavy lifter, follows the same philosophy, with 24 main wheels and kneeling nose gear.
That kneeling gear lowers the cargo floor for direct loading, opening airfields where a Boeing 777 would never operate. Steeper approaches, firmer landings, aggressive brakes, oversized flaps, reinforced gear. Every trick costs the passenger comfort, silence, and smoothness, which is why these design choices exist only on aircraft where no paying passenger is ever present at all. But the true payoff of these design choices only becomes visible where a runway is not luxury, but lifeline. Anchorage, Alaska, winter, temperature -20. The runway is coated in a thin layer of frozen slush at dawn. A Boeing 747 freighter, weighing nearly 340 tons, breaks through low cloud on final approach. Crosswind is gusting to 30 knots, visibility under a kilometer. The captain crosses the threshold at 142 knots. The mains touch down. Spoilers deploy. Reverse thrust roars. The brakes bite through the anti-skid system with mechanical precision.
In just over 1,600 meters, the aircraft is stopped, cargo intact, crew unharmed, and the runway still clear. A passenger 747 in the same conditions would need 2,400 meters, and the flight would likely be diverted. Consider a C-17 on a resupply run into a forward airfield, fully loaded with 77 tons of cargo. The runway is packed dirt, 900 meters long. The approach is steep, nearly 4 degrees toward touchdown. Touchdown is deliberately firm, a controlled slam, not a kiss. Reverse thrust engages before the nose wheel drops. The aircraft stops in 600 meters. It turns, taxis, unloads, and takes off from the same strip. This is a routine mission. It happens daily. Now, here is the anchor number that reframes everything after. A purpose-built cargo aircraft operates from runways roughly 50% shorter than a passenger jet of comparable weight. And yet, it still carries 90% of rated payload.
That is not small. It is transformation itself. The economic ripple is enormous. Countries that could never afford full-scale airports can build short cargo strips affordably. They immediately connect to the global economy. Mining companies operate in regions with no road infrastructure whatsoever available. Humanitarian agencies reach populations otherwise cut off entirely. The freighter is quietly one of globalization's most powerful tools. But here's the thing. This remarkable advantage is now quietly under threat from forces few travelers ever notice. The real reason cargo aircraft land on half the runway is not weight, not brakes, not pilot skill. They land on half the runway because the mission was defined differently at the original drawing board itself. The airframe was told from the beginning that it would suffer more, be pushed harder, endure worse conditions. It would land where nothing else in commercial aviation could safely operate. That was the entire design mandate.
Runway length is not physics. It is design, and that design is shaped by one factor, the human passenger. Every airliner seat is, in a real sense, a meter of extra concrete. Every meal service adds more runway. Every overhead bin. Every regulation about smooth touchdowns and gentle turns. Every comfort demand lengthens the concrete required. This is why passengers will never receive freighter treatment. The regulatory framework protecting travelers also lengthens their airfields.
Crash safety, comfort standards, noise limits, the same rules that guard passengers force jets into longer, costlier runways. The hidden cost of a comfortable flight is baked into every ticket, measured in part in kilometers of pavement. And yet, this trade-off may not last forever. The next generation of freighters is preparing to go even further. Consider what emerges in workshops of Toulouse, Seattle, Nagoya, and dozens of startup hangars across America and Europe. Electric short takeoff cargo aircraft designed to operate from strips as short as 500 meters of prepared surface. Hybrid electric freighters use distributed propulsion, multiple small motors along the wing, each independently controlled, generating extraordinary lift. These wings generate lift at speeds no conventional jet could survive, opening runways once considered impossibly short. Autonomous cargo drones, some the size of a small airliner, are designed to fly without any human pilot aboard.
They land on airstrips too short, too remote, and too dangerous for any human crew to safely operate. Companies in Africa already run trial routes with these aircraft, delivering medical supplies to villages that never had roads. In the Arctic, prototypes are tested that land on frozen tundra without any prepared surface at all. In Southeast Asia, autonomous freighter designs promise to slash logistics costs for island nations by 80%. If these systems scale, the geography of global trade will be rewritten, remaking commerce across every continent on Earth. Regions considered too remote, too poor, or too rugged for air freight will suddenly become fully connected. Supply chains reroute. New economic centers emerge in places where no economy currently exists, transforming forgotten frontiers. The map of the world, measured by logistics reach, will look entirely different by the middle of this century.
And the runway itself, that long, expensive concrete strip that defined aviation for a century, may vanish, replaced by short paths, dirt patches, floating platforms, and even inflatable landing zones deployed anywhere on demand. The infrastructure that once dictated where cities could grow will no longer hold that power. Aircraft come to cargo. This is the quiet revolution hiding inside a very old question about weight, thrust, and runway distance. Why can a heavy freighter land on half the runway required for a standard passenger jet? By design. The industry looked at constraints of comfort, certification, convenience, and for cargo chose to remove them entirely. In removing them, engineers unlocked an entirely different kind of flight. Subscribe to continue exploring how our world works. The runway may soon disappear entirely. If these machines surprised you, more films await. How humanity outsmarts nature. How bridges hold up mountains, how tunnels breathe under oceans, and how aircraft rewrite the geography of trade. The next film explores vertical lift cargo, aircraft that need no runways, opening trade routes across untouched terrain. Subscribe to continue the investigation. The next chapter of flight is